All right. Well, good morning. My name is Kat Kornegay. I'm a PhD student at Stanford University, and today I'm going to go into an application of melanin, specifically talking about the synthesis and multiphysical characterization of melanin-rich mycelium aerogels. So that was a mouthful. I really want to, I like to abbreviate that full thing to mycogel, and we can really break down the mycogel into three parts: mycelium, aerogel, and melanin. And I'm going to go into some of their benefits and ultimately talk about why all three combined are a great type of material. So first, we'll start with mycelium. So mycelium is just the vegetative root of the fungi. If you think about The Last of Us, that's like the really scary villain that really allowed it to all. It's like a very interesting network system. Some of its really cool properties is that it's a lightweight material. It has radiation capabilities, also tunable properties. And this is not just a theory. We've been able to actually create material structures from mycelium. We've been able to do it more than just on the small lab scale. Some of my collaborators have been able to build furniture where you can sit on it. And eventually we want to be able to create large habitat scales, both on Earth and on the moon, which is a really cool concept, which I think you'll be hearing about more this afternoon. But just some of these really interesting applications of using mycelium as a material structure. So how do we actually create this material structure? We do this by creating a biocomposite, and there are three main parts to its production. So we have inoculation, cultivation, and then the drying part. I'm just going to go into the inoculation part as an example. And so when we look at the inoculation step of creating this biocomposite, we have two main parts. We have our feeding substrate, which right now we're using some sort of agricultural waste product. In this case, it's sawdust. And you mix it with a mycelium species, whatever fungi you want. And the fungi will feed on that substrate and bind to it to ultimately create this really cool, solid biocomposite. And so there's a lot of research that has been done on the biocomposite part, looking at agricultural products. And one thing that we're interested in is how can we make this lighter, while also keeping its mechanical properties. One way to do this is through the second word, using the use of an aerogel. So when we go back to this inoculation step, instead of having the sawdust as the feeding material, we're using a hydrogel and maybe even some form of a yeast or food to allow the mycelium species to grow. And so what is a hydrogel? Basically, a hydrogel is just a mix of some polymers where you can create sort of a gelatin, mostly water material. So you can think of like boba, that's an edible type of hydrogel. And from that, there's many types of techniques that you can create aerogels with. And it's basically just sucking out that water and creating a very porous, lightweight material. So this is just a great diagram actually depicting how we go from these initial precursors to the hydrogel to finally our aerogel. Some of the great properties of aerogels is that, again, it has a high porosity, it's still very, very lightweight, and some of the materials allow it to be thermal, have low thermal conductivity. Because of that, some of its applications are insulation, packaging, and even storage devices. I was able to find this really cool example of actually finding an actual fungi, a mushroom, dehydrating it and making that an aerogel. And they were able to make it super elastic, and very protective of water, against water. The difference between the aerogels that we're working with is that we're actually using that hydrogel material, that aerogel, that gelatin material, and mixing it with the mycelium to create this low density, high porosity material. So I've talked about the mycelium, I've talked about the aerogel, and now I'll talk about the melanin, which is the focus of today's group. And so Andrew gave a great explanation of what exactly melanin is, so I don't have to go into that. But again, some of its properties is that it has a broadband absorption, it has thermal regulation, and a high refractive index. And because of these really cool properties, it has applications in radiation shielding, bioelectronics, and energy harvesting. And fungal melanin in particular is also really great because it can live in these harsh environments that we talked about. So some examples of that is that we're actually able to see it grow actually on the walls of the International Space Station, so in space. And we've also been able to see it in these Chernobyl radioactive sites, just showing the strength of melanin and its ability to sort of grow anywhere. So now you understand all the three components of the microgel, and so that makes this slide a little bit easier to understand. The melanin-rich mycelium aerogel, and we were really inspired by the shells of turtles and snails. So when you think about these shells, they are very durable to the outside environmental environments that can really protect these animals, but they're still lightweight, they're still durable, and they allow the animal to function really well. So that's one of the thoughts that we were thinking about when creating our microgels. And in addition to that, one of the things that we're thinking about of making a sustainable material is how close can we get to this zero waste manufacturing as possible. One way we're thinking about that is in this dehydration step, from changing it from a hydrogel to this aerogel, how can we reclaim that water and maybe even reuse it to make more aerogels? Another thought is when making this material, how can we make it as compostable as possible? What kind of ingredients can we use to make the material completely biodegradable? And so in that, our project has 4 main tasks. The first one is ideating the synthesis. So how do we actually make these aerogels? What kind of materials that we use to put it together? The second one is assessing zero waste capabilities. So again, this is ways that we can reclaim the water, ways that we can make the material compostable. Task 3 is testing and characterizing the properties. So this is such a new and interesting material. What does it even do? How does it function? And why does it function that way? So that's what task 3 does. And then task 4 is to accelerate this translation from just this lab scale sample to a more everyday material. So some of the properties that we can use and apply it to is packaging. We can use it as thermal insulation houses and things of that nature. So how can we start producing it from the small scale to a mass scale operation? Today, for sake of time, I'm only going to talk about task 1 and task 3, because that's also the main focus of what I'm doing. So how do we create this microgel, and how do we actually characterize it? So we'll start with task 1. So I mentioned in order to create aerogels, we have to start with a gelatin hydrogel material. Right now, we're using sodium alginate. Again, I mentioned that's the boba that you eat. We use this because it's fast growing. We know it's edible, so it's safe for humans, as well as biodegradable. Another option that we're thinking about is, I'm going to butcher the name, polyacrylamide. That's in diapers. So it's very absorbent, has really strong mechanical properties, but it degrades toxically. So we're trying to balance the scales of great material properties while also making it, again, as close to zero waste as possible. And so these are just a couple of examples of the hydrogels that we plan to test in our sample. Another thing that we're trying to work on is the actual synthesis technique, changing this into an aerogel. Currently, we're using the freeze drying technique. And the way that this works is you have your hydrogel mix of melanin and mycelium. You completely submerge it in water, so it's filled with water. Then you freeze that material. You place that frozen material in a vacuum. And in that vacuum, you'll have that water sucked up. And so in place of that water, you have these large porous holes that create your aerogel. So on the left here, you see some initial samples of hydrogels that just have melanin in it. And then you see the freeze-dried process of your aerogels here. And so these are sort of the materials and thoughts that we're trying to really hone in on of what will give us the best microgel available. And then finally, moving on to task 3, we want to be able to test and actually characterize these multi-physical properties, understand how this material works. So this is just an overview of some of the characterization tools that we can use. There's so many more. I'm a material scientist, so I kind of geek out on the characterization part. But some of these are the 4 main that I will be looking at: chemical, mechanical, optical, and microstructural. So the chemical will allow us to understand its like molecular bond and molecular structure. The mechanical, we will be able to understand the strength properties. Optical, we'll be able to understand sort of, we were talking about like the thermal properties and sort of how much it can protect from like UV radiation and even larger scale radiation or other types of radiation. And then microstructural, just really getting cool images of what it looks like on that micro scale, and then eventually connecting all of these characterizations into how it functions as a material. Today, I'm only going to talk about the top two, chemical and mechanical. And these are just going to be examples of characterizations that I hope to do in the future. So first, chemical characterization, I mentioned that it'll allow us to understand the chemical composition, the actual molecules, and really what makes a mycogel. This is an example of infrared spectroscopy scale. So you're able to connect the peaks that you see with the actual biomolecules within the mycogel, or in this case, within a mycocomposite. And this is just confirming that what we see is actually the material that we want to like produce. So chemical characterization is a good first step of categorizing exactly what your material is. The second step is mechanical characterization. And this, again, allows us to understand the strength, the fracture limits of the material. And so currently one of the tests that we're doing is compression tests. So I always like to say that like I break all the materials, and that's my favorite part. I'm doing very destructive tests, but really understanding exactly why they're breaking, what kind of different modes that we can use, and really take it to its limit to understand exactly what's going on with the material. This is just a stress strain curve that you can get to understand its how its compressive strength, so how high of pressure you can go before it starts to break, its elastic strength, different things of that nature. And so to recap of all the things that I said, I'm working with this really interesting material, melanin-rich mycelium aerogels, or mycogels for short. We can use this in really great applications, both on Earth and in space, but thinking about thermal insulation, thinking about packaging, things of that nature. We're also working to make make the manufacturing as close to zero waste as possible. I'm thinking of ways like water reclamation and making it compostable. And then on the bottom, you see my 4 main tasks. And today I talked about how we will actually possibly create the mycogels, and how we'll actually characterize the mycogels. Finally, I want to acknowledge that it is not just me on this project. I say we because it's a big team. And these are all some of the people who are doing a lot of the work that we plan to and hope to accomplish with this project. So with that, thank you.